problem that involves more than 3 charges. Just to show that this works in general. Let's say that we have a cube in which this charge is the same as this charge. Make sure I do this the way I want to do This charge is the same as this charge, and these 2 charges are the same. Okay, so the charges at the corner, opposite corners, are the same. And so let's say if Q equals 10 to the minus 5 coulombs, let's find little q such that the force on the upper left-hand corner is 0. Let's say upper right-hand corner. Let's go with this one. Okay. And so what we have then here is, and let's say that this distance here is d, 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 and d. So if we need to, I'm not sure whether we're going to need to. Might not. But let's just, to make ourselves comfortable, let's say d is 1 meter, just in case we need it. It may cancel out. We just have to see how this goes with the math. But we want the net force on that upper right-hand corner, to be equal to 0. Okay, and so what we can work with so far is this force. We know what that force is already. And so then what that tells us is that these 2 together are going to have to cancel out that force. So that's the way that I'm initially conceptualizing the problem. I'm seeing that there's something that's already given. That's the charges in the corners here. And so associated with that, then I'm going to have a net force on, this is 1, 2, and 3. This would be F3. It's going to point that way. Okay, and so we want to cancel that out with the effects due to these 2 charges. Okay, so do you think these charges are going to want to be positive or negative? We want to cancel out F3. Negative. They're going to have to be negative. Okay, so that's good. At least we know that much. We know they're going to have to be negative. And so we can also, this is really super important, is to draw the vector diagram. If you don't, I mean, I would never try to do a problem like this without drawing the vector diagram first. So I'm going to have an attractive force here, I'll call that F2, and an attractive force there that I'm going to call F1. But notice that I'm not drawing any vectors on any of these other corners. I don't need them, because I want to know what's happening to the upper right-hand corner charge. That's it. So that means that my vector diagram is confined to this guy here, and not to any of the other ones. Okay, and so if these are the same charge over the same distance, what can we conclude about the magnitudes of F1 and F2? They're going to be what?
Equal 90 degrees.
They'll be equal in magnitude, but yeah, they'll be pointed in different directions, 90 degrees out. So here's my F1. Here's my F2. So I'm just going to call these two my generic values for F. And then what's this going to be then? Well, that's going to be, if this is F, and they're both equal in length, then what kind of a triangle is this?
Right.
What kind of a right triangle?
45 degrees.
Good. 45, 45, 90. That's a special kind of right triangle in which the x and the y components are the same. Okay, and so if this is F, then by the Pythagorean theorem, the hypotenuse has to be the square root of 2 times F. Does everybody see that? You can just do the Pythagorean theorem if you don't believe it. The square root of f squared plus f squared is equal to square root of 2 f squared. That's equal to square root of 2 times f. Right? Or in your basic right triangle relationships, I always learn that a 45, 45, 90 is 1, 1 square root of 2. Right? So if you remember that and the 30, 60, 90, that'll get you through half of the examples that we give. Because I like to choose simple angles whenever possible. Okay, so now I know that this distance is the square root of f. Now how does that align with f3? Doesn't it exactly cancel in the opposite direction? So my condition then is that what I want is the square root of 2 times f to equal f3. This isn't the only way to do the problem. The other way to do the problem would be to take f3, break it up into x and y components, then set the x components equal and opposite, and the y components equal and opposite. You'll get two redundant equations, but you'll end up with the same answer. So you could do it that way, and that would be also totally legitimate. But I'm going to do it this way. So f3 then, what's that? Well, that's k times q1 times q2 over the distance. That's the square root of 2d squared. So that's over this distance. This distance is d, but again, this is a 45, 45, 90 right triangle. So this distance between these two charges is the square root of 2 times d. It's a little longer than the side lengths because it's the length of the diagonal. And then f is going to be equal to, well, what do we get for f here? That's just going to be k little q big Q divided by d squared. So that's going to be my f1 and my f2. But that's not quite what I want. I want the square root of 2 times f. So my condition then, square root of 2 times f is going to be square root of 2 times k little q big Q over d squared equals f3. So that's going to be k. I'm going to write the q's as q times q so I can cancel one of them out more easily. Divided by square root of 2 squared is 2 times d squared. So that's my condition then on little q. I can cancel out the k's, cancel out the d squareds, and I can cancel out the big q's. And so what I'm left with then is little q is equal to big Q divided by 2 square root of 2. And so that's the same thing as, well, this is square root of 4 times square root of 2. So that's the square root of 8. think we did that on another problem just recently. That was 2.82. This is big Q divided by 2.82. So big Q is equal to 10 to the minus 5 coulombs. Then little q is going to be 10 to the minus 5 divided by 2.82. And what have I forgot again? That it's got to be negative. Okay, so the fact that I set these magnitudes equal means that I have to use my physical intuition to realize that that has to be negative. So this is 3.546 times 10 to the minus 1 times 10 to the minus 5 with a negative sign out in front, or 3.546 times 10 to the minus 6 coulombs. So that's my final answer, the negative sign. But it's just whatever that other charge was divided by square root of 8, or 2 times square root of 2. Any questions?
How did you get lowercase q is equal to uppercase q over 2 root 2?
I set these two equal and solved for little q in terms of big Q.
I see.
And then after all the smoke cleared and most of those things canceled, there was a couple of numerical factors left with the big Q. That just got.
Gotcha.
Any other questions? So I think hopefully the algebra isn't the problem, but I know from experience that it is the problem. That maybe 80% of the errors are algebra errors. They're not calculus errors, they're algebra errors. So watch the algebra when you're doing these things.